I'll try to do more application stuff, I guess, at this part. I chose this one because this application of machine learning data mining for detecting PDF malware has seen many interesting things like attacks and defenses. For everybody uses PDF, so I don't need to go too much detail on the PDF. But basically, PDF has some kind of certain header, right? And it's a document format. And in this document format, you have a header, you have a body, you have some kind of reference table, and you have some trailer information. And it turns out that you can use PDF to hide malware in it. And there are some PDF malwares out there. Why? Because in PDF, you can embed some JavaScript in it, and you can add some other code in it that can be used to download malware, or it can contain the malware payload. And this is usually done by maybe having some kind of JavaScript. They could have some malformed objects, some kind of malicious patterns, and it may have some kind of suspicious actions in it. So now the challenge is, given malware, no malware structure, and potentially attackers who are injecting malware into these PDFs, can you detect PDF document with exploitation in it? Can you detect PDF document with malware in it? And of course, since we talk about machine learning, why don't you use the machine learning, right? And this is a work, again, the citations are there. What they've done is they've done some analysis on the documents, and then they're trying to come up with features that can work well even on encrypted documents. Some of the PDF documents could be encrypted, and some of the features inside the PDF can be encrypted. And then, but still the encryption leaves the structure and metadata to be intact. So here, the authors or the people who done this project start with PDF, and they wanted to figure out what features we should use in our machine learning model so that we can detect malware. And as a part of it, they want some features that depend on the structure and metadata, not the content, because content could be encrypted because the PDF can be encrypted. So they start with feature, and then after these feature things, they come up with this kind of classifier. And then in their case, they have three different things. One, try to distinguish, given a PDF, whether it's benign or malicious. If it says benign, it's a benign PDF. If it says malicious, then they have another classifier. They have what they call it opportunistic malware versus targeted malware. And then they try to differentiate these two. So each of them are a machine learning classifier. In this case, they use something called, I think I have it next slides, random forest. They use something called random forests, our machine learning model. So basically, they extracted features. I didn't go into details of the features. And then they applied machine learning techniques. And what they showed is that, OK, the techniques are here, is that they have this many instances of malwares. They have like 5,000 benign. They have these targeted ones and opportunistic malware. And then they test on hundreds of thousands of documents. And then what they are saying that these are the training time and the error rates. And as you look at it, the error rate here is, in this scenario, random forests work very well for them. And it was less than 1%, okay, and compared from the support vector machine. One issue in support vector machine, you need to train, you need to have right kernel, right parameters, so it requires a little bit effort. I don't know whether they spend on it here. But they got a super duper accurate classifier. 99.8% accurately can classify whether a PDF is a malware or not after training these instances. So that was the result. And the reason I chose this example is that then they look at, oh, sorry, I thought I finished it. Then they look at Then they look at the false positive, false negative rate. And then as you see the success true positive, in other words, malware classified as malware reaching 0.999. And they have false positive rates also very, very small compared to traditional things. So they achieve fantastic success in applying machine learning technique such as random forest to get super results. But remember we talk about attacks, and then there is an attack paper for this previous machine learning work. Okay. Now what they try to do is that what happens this malicious noise? Can we, in practice, remember we talk about some theoretical work trying to change the instance so that it can pass the classifier. So what does this mean to make it the classifier? So what they've done is they insert dummy content into PDF files. It turns out that if you, I'm not an expert on PDF and so on, but my understanding is that if you put some certain contents in PDF in certain way, PDF reader will avoid it. Okay, so it won't change how the PDF will look, but you can change the features that's being used by the previous system. The previous system were using features like average header length, average body length, this and so on. So they can insert this dummy thing to decrease the score returned by this PDF rate, which is the previous work that they showed to work fantastically on this PDF malware. So what they are doing is that this is the original PDF, and then they inject this content, and it turns out that PDF readers jump from trailer directly to cross-reference table, and this part is totally not shown. So therefore, in this scenario, the cost of change is almost zero once you find the cost, because it doesn't change how the PDF look. Because if you change how the PDF looked, then it may have impact. Now they look at a couple of attacks. One is called the Mimicry Attack. This is a very common attack. So you try to look like a legitimate one, and you transform sample until it mimics a chosen benign sample. And then there are some specific attacks, especially applicable for SVM and neural networks, because it requires, it's against for gradient descent and kernel density estimation type of techniques. So if you know a certain classifier such as SVM, maybe you can tailor how you modify or what the content you inject. So this one is applicable for any classifier. This is for specific classifier. So here also there was this question like what the attacker knows. They look at different scenarios. In the baseline, the PDF really, the function, the previous work, really functions as they claimed. So it's like, again, success ratios over 90%. This is like error bound. So in some cases, it's very, very high. So now they look at different scenarios where attacker knows different things. In this scenario, attacker knows the features. Okay. In this scenario, attacker knows the features and the classifier. In this scenario, attacker knows features and the training set, some of it. And in this scenario, attacker knows feature, training set, and the deployed classifier. Of course, not surprisingly, they show that the more the attacker knows, that can increase the success rate against this classifier. So if you recall, original was working 90+% accuracy, 95, 99. And now by this mimicry attack that knows the features, the training set, and the classifier reduces the success rate on average to 30%. Okay. Of course, even if you know the features that helped a lot, from like 90% to 40%. This targeted attack, if you know the classifier type and assuming that and target based on that, then it can help you a little bit more. Okay, so basically all of them would have classified many malwares as benign. Of course, how do you protect against that? In this work, they suggested maybe we can, in the training set, we can simulate some of the attacks already. And this way, our learned classifier could become kind of vaccinated. So the idea is coming from the vaccination. So if you recall, in vaccination, they sometimes inject some virus samples to your body immune system learn about it, and then it's getting ready. So the idea here is maybe we should do something like that for the machine learning and inject some things. But it turns out that if the attacker knows this, attacker can bypass it again by changing the attack. So it wasn't very helpful. So now this knows the features and this knows the things, and they randomly change it, or they tailor their attacks based on the features and so on. The follow-up work tries to look at it as too much text. I will put the slides online, and I try to put lots of text on it so it's self-contained, but I pass some of them so that I can explain with the feature. But the slides will be available, so when you read it, it will make sense. So there are some explanation slides in between that I'm passing. So what they try to do is that, can we automate this process? Instead of trying to do these dummy things, can we totally automate? This is another work, I think, from last year in NDSS. And then what they are doing is that they kind of trying to combine genetic programming to find automatic samples for evading attacks. And what they are doing is that they have this malicious samples, they have this benign samples, and they created this population. From this population, they have this target classifier. Target classifier is like the PDF rate. And they have an oracle. Oracle is basically, in this model, they want to figure out whether the modified, remember, they have a mutation of the PDFs. And the oracle is used to figure out, after mutation, malware is still a malware. Because your mutation, automatic mutation, may change malware, and it may dilute the malware's function. In this work, they used for oracle some kind of virtual machine, okay, to see whether the PDF will still try to, infect the machine. And then they have a fitness function, and then the fitness function is that if the oracle says 1, like it's a malware, then what's the score the PDF rate is giving to you? And then if the oracle says not malware, you just assign some fixed low score value to it. And then if you find a variant that passes the target classifier, then you have a success. No, then you select variants, you do mutation, and you continue this loop until you find a thing. So here you have like insertion, deletion, replacement. So they have a couple of mutations. And it turns out that they run it on many malwares. What happened is that they could make, for PDF rate, this is the number of hours it took them to find evasive samples. And it turns out that for each variant, they managed to achieve 100% evasion rate. So for each malware, they find a variant of that malware. Although it took them some time to find it, okay, that will bypass that classifier. Okay, and similarly, there is another one. It turns out this HeDOST was designed to be more robust to resist this evasion attacks. Still, they managed to find 100% evasion rate, and it turns out that in a quicker time, interestingly, for this scenario. Like in 2 days, they managed to find, for each of the malware samples they have, they find a variant of it that will bypass this classifier. So again, of course, the issue is, I think from cost point of view, is that it looks like the features are very easy to modify for the attacker. And therefore, the classifiers couldn't work. And usually you will find a way to do it. So they look at their work. They think that if they didn't have the classification scores, because these things will give you a score of how malware, or what's the probability of this PDF is a malware, it turns out that their technique adaptation will maybe less successful. And then they also think about like maybe you can select more robust features and so on. And still, this selecting more robust features, I think, is an active research area. Another example of this adaptive techniques and so on is on crowdsourcing, which is also a hot topic. People applied machine learning techniques to find malicious behavior on crowdsourcing. And their idea is, can you detect attacks, like poisoning or evasion attacks on this scenario? And they look at, for example, Weibo, I think Chinese microblowing network, and they look into users there.
Can you explain just the two attacks?
I will explain it to you in the results. We will come back to attacks in a sense. So basically, what they want to do is that they have here basically this craft turfing is apparently assume you wanted to buy fake likes, fake reviews, and so on. You can hire these crowd workers online, and then they will like your thing. They will post comments for you. So now the question is, can you identify these malicious workers online who do malicious stuff? And they try to look into microblogging sites. They have this many known craft turfing guys, this many authenticated legitimate users, and they have this many users. And then these are the number of IDs they have. And then they try to classify these accounts, these active accounts.
If you need any help, I can help you, user.
Thanks. Into, again, these techniques, SVMs. As I mentioned before, DL was cool. The traditional things you would see is an SVM, decision tree, and random forest. So it turns out that they could look into these data sets. They sampled 20K turfing accounts. These are known accounts, and then 28 authenticated accounts, which are nice accounts. And then naive Bayes is not very good, but naive Bayes is a very naive method at least. J48 is basically a decision tree and a common, very important variant. And the random forest is basically many decision trees. And the random forest gets a very good rate as well initially in classifying the turfing versus the authenticated or automated. Similarly, they run this on 20K turfing account and 20K active accounts. And then they try to distinguish active versus turfing. And then they manage to get, again, a couple of % error, false positive, false negatives here. So very low error rates. And now they look at evasion attacks. And then they look into that is per worker, the worker wants to modify its data so that it won't be classified correctly. And then they look at per worker strategy. Per worker, each worker come up with a strategy by itself to evade the thing. So if the worker changes its behavior, for example, like number of tweets or number of actions it got, or number of times it logs in, or when it logs in. And then they look at the global version. And then finally, they have the feature-aware one that knows the most important features for each classifier. And then what they look into is that if each worker can change 4 or 5 features, then it depends on the classifier function, they can evade the detection with very high probabilities. And it depends on the function itself. For random forest, remember, random forest was the most successful one. And in the random forest, each decision tree uses a randomly selected features. Sometimes it helps, as we see, and it makes it slightly more robust compared to other techniques. And you see similar results in different type of evasion attacks. So therefore, they show that, like the similar domain as an example, they can evade this based on the known features. Here, this is global. Global means that in everybody, the same set of features are changed, so that it required more number of features change. But this is per worker. Each worker optimally changes. So that's the reason you need much less features. This is the same features for everybody. And the future importance is that this is just the important features based on importance criteria such as information gain. So they look at more practical ones because the previous one requires solving optimal things. And then even the random evasion strategies work well, but of course you do more features because it's random. Value distance evasion is that the attackers know few good accounts and tries to look like them. And then it has certain distance measures for it. The detail is not that important, but in other words, you try to mimic under certain cost functions. So again, not surprisingly, if you have certain number of features, then the number of workers evading detection increasing. And if you look at it, basically, here 20 features give you 40% evasion. For, let's say, for random forest, 20 features will give you around 50. Here, 20 features for random forest, it turns out to give slightly less. So even random strategy turned out to be somewhat effective. They also look at the poisoning attacks. Remember, we talk about the test time and training time. In this work, the reason I chose it, they look at both attacks at the same time. And then they look at the false positive rate when the ratio of poison to turfing. Settings turfing is a bad class here. And of course, if you can poison almost the same ratio, then the false positive increases significantly. Let's say it's less than 0.01 to, in this scenario, almost 10%. And this is for all workers setting, active and everything. They seen still similar jump, but of course this is quite significant. Ratio 1 means that if you have 10,000 turfing examples, you have attacker can add 10,000 fake instances. So I think it's much harder for attacker to have such high ratios. They look at different settings like injecting accounts with certain number of tweets or injecting accounts with less followers, and specific type of injections seem to especially in this scenario, gives much better results. So you can tailor the injections and attacks accordingly. I'll skip this one. Here, instead of adding data to the training set, they look at modifying the data in the training set. So in that scenario, they also show that they could increase the error rates for different profiles based on different type of feature selections. So these are two examples showing that when it's applied for cybersecurity problems, attackers can attack SVMs, random forests, and so on under different assumptions, both in the test and training. Recent focus, I would say, yes. And yes, sorry, let me go with her.
Can you maybe give an example or some examples of different features that are used, like in the spamming example, please?
In this scenario, the features they used was these fake workers, like the fake users, they like your profile. For example, how many tweets they have done in the last 24 hours, how many logins they had, how many followers they have. And then some of the things they change. For example, they can follow more each other and they increase their follower number. So that's a change. Or they can do more retweets, for example. So those are the kind of the features that they manipulate.
So they're looking for the spammer and not the spam.
They're looking for, in the previous example, they were looking for the spammer, not the spammer accounts, basically, or fake accounts versus real accounts. These are like buying likes, for example. I think they sell it, I don't know how many. I think like for $20 you can get 1,000 followers or something on LinkedIn if you're into it. So they sell such things. So you try to figure out such accounts. In the previous PDF malware scenario, the PDF was the same. You were just changing and adding this dummy part that's not rendered by the PDF reader. You add stuff, you delete bytes from it so that it will pass the classifier. But still, it looked like a legitimate PDF.
And then the features were based on?
Based on the, yeah, okay, I would, yeah, characteristic of the PDF, the features were there like the length, header length, total bytes, average byte. I mean, not average byte, they look at the like average header length, average cross-section length. Does it have JavaScript in it or not? Does it have, what else in those features? Those kind of features. Yeah, I will add those examples to slides before I post it so that if you download it, you will see some examples. Sorry, let me go with the order Michael was.
So are there general trends regarding which machine learning scheme is better? Do they deduce that random forests are inherent?
I will have some comments at the end. Let's come to that. I wanted to separate them to the end because they will be somewhat my personal beliefs. So these are like the published work. So I'm just mentioning those published work. At the end, I will have such comments on that.
What we see that random forest is better than others because it does some sort of overfitting.
And it also do random feature.
Much easier to avoid it once you know this overfitting. So that's a catch game all the time.
Yeah, that's the reason I think it boils down in these two examples. There were examples where attacker easily manipulated the things. But for example, if you think about malware, clearly anything, according to me, anything that depends on the binary sequence of the malware, whatever the machine learning technique you use, there is a way to avoid it. Mm-hmm. But a malware who tries to, let's say, exfiltrate sensitive data needs to access that data, for example. And that feature cannot be changed by the malware if you want it to be a malware. So that's the reason I think it will boil down. Of course, some techniques are better than another, as we've seen. Even in random forest, they require more effort in this scenario. But end game, it will behave based on, I think, more of the cost for the attacker. So yes, there's this catch part here, but I think the solution would be to really choose robust features. It will have moved to of course.
Just,
yeah.
you one way or another.
Yeah. You have a question? Okay. Okay. I just wanted to also talk about DNN. This is the most active work happening in this space, at least the last security conferences. For those who doesn't know DNN, this is at least the way I see it, is the neural networks on steroids. And then, of course, they have lots of new innovations done, like convolutional neural networks. There is a very nice survey of it appeared in Nature a couple of years ago. I think it's a very nice overview of deep learning by Hinton, I think. But usually you have input vectors and you have these hidden layers. And then I've seen, and then some of them have, and these layers have different properties. Some of them can do convolution. Some of them have different nonlinear functions in it. And then you have many, many layers. And the deep comes from this fact. So this could be very deep. So I think 35 layers, 35 depth ones are quite common in some image processing things. So you have like 1, 2, 3, go to 35 deep and millions of nodes in it. And then there is some kind of last hidden layer, and then there is this soft max layer. Anyway, think more of those layers. And there is this neurons, as I mentioned, neurons have different flavors, different type of them. And then you have some weights. There's a weight associated with each thing here. And deep learning basically tries to give set of samples, like images. By the way, at least this is my 2 cents based on my own experience. If you have small number of dimensions, like less than 50 or something, and then the deep learning usually doesn't give you much better. But for image classification, where you have, let's say, 100 times 100 pixels, which is 10,000, or some text classification, deep learning works fantastically. But if you want to go into deep learning business, buy a GPU-based machine, because I try to run on my desktop. It takes days, weeks to train a simple one. So all I'm saying is that although it's a very cool thing, if you're not into image processing, it may not worth it. So try SVM and random forest first, and if it doesn't help, then go into this. But anyway, so this is a traditional deep learning things, and there's a very active research area, and by no means I'm an expert on it. But basically, what happens is that there is a recent work showing that you can modify the input slightly to change its classification. And here it turns out that those are very subtle. So this was one of the first attacks or things against this. So this is the original image, and it's correctly classified as a bus or school bus. And then you add some kind of noise. This is this random noise, and this is the final image. And if you look at it, these two at least look similar to human eye, I guess, right? How many people can differentiate these two? I don't know, at least in this one. And it turns out that this will be labeled as ostrich by a deep learner. So when you add this noise to it, and similarly, these are all correctly classified, but when you distort like this to make it this, I don't know what has changed in this picture. It's very hard to see. Again, the deep learner misclassifies it. So how do they come up with this noise? There are different techniques and so on. Another example would be this. And then what they've done is that this is, I will put the citations there. In their case, they have this panda. This is from Goodfellow. They have panda with certain confidence. It's classified as X. And then they add this noisy picture, and they do it based on the this is the deep learning techniques usually do this stochastic gradient descent based on search based on the derivative of this function. So they are trying to add noise according to that derivative computed for this image.
Nematode.
Sorry?
Nematode, it says.
I mean, this is classified as nematode with this confidence. When they combine these two with some certain weights, this is classified as gibbon with 99.3 confidence. So if you look at this picture and this picture, they look quite similar. So deep learning, now people try to use deep learning for cybersecurity. I just saw recent work, they apply deep learning as well. But most of the, at least attacks until this point, were focused on images. As I mentioned, images are a very important use case for deep learning, and where you see like image, video, neural text processing, especially natural language processing. Deep learning has shown substantial improvement compared to other techniques. So therefore, this is an example. This is relevant for the scenarios for cyber-physical systems where the self-driving cars learn how to go.
But in these works, you have to know the model and the exact weights of the internal structure of the network. It's not like a black box that you pass one image and say, oh, okay, maybe I'll try to trick it.
Sure. There are some work, so the question is like this assumes a model, yes. And there were some work, I didn't put them there. They do this search mechanism. They keep, if you can keep querying it,
yeah, okay.
and then if you can get the probability scores, you could compute these things yourself after some queries. Because you give an input, you know the input, you know the output, and then you change input slightly and you know the output. So you can compute these statistics after some samples. Yes.
Has anybody tried these attacks on like actual cameras?
Yeah, they tried it. I should have put it maybe, but again, I have only 3 hours. So basically, the one attack they've done is that they try to make people look different. And the attacks they did is that assume you wear a different type of glasses, but assume it's not like my glasses blue or white or black. Instead, you can put your glasses, make like pixels like this. And then they managed to change one, like a grad student, I think it was from CMU, grad student into Brad Pitt, maybe, like recognized as Brad Pitt, by changing just the eye area. So they've shown it's doable. But of course, if you try to go to, let's say, the Ben Gurion Airport with such eyeglasses, I think you will be you will be picked up very quickly. I can assure you that. But I mean, that's just an example of that. So how these techniques usually work? They do this neural network architecture, and then they have some kind of perturbation selection techniques, different optimizations come into place, and then you check whether it works. If not, you can go back and you modify it. And eventually, here, this is the classified sample was 1, right? So this is, by the way, in this setting, this is an image of 1, the number 1, or digit 1. And our goal want to make this digit look something else. Eventually, it found that if it changes this change and this change, it became 4. Okay, and how you find the modifications? Again, I explained it. So this Goodfellow attack focuses on this fast gradient method. It computes the gradient of the cost function with respect to neural network. There is another one that looks into Jacobian of f. This is usually make it differentiable, this deep learning network, and you can compute this Jacobian of it. And then, but they also have saliency maps. In other words, they try to look at how certain feature groups impact each other. And with respect to each component, and then they use it. So again, it requires some understanding of how input works. And in these two types of attacks, in one, it perturbs all dimensions by small quantity. If you look at these attacks, like all of the pixels are modified with some quantity. And there are other one, this peppermint one, that looks into the salience maps that assign values to combination of input dimension, indicating whether they will contribute better together or not. So this requires more search, a little bit more search. But still, you don't need to change all the dimensions. You can get away with selecting a limited number of dimensions to perturb. So now, what does it mean from a point of view? So they define this robustness as a measure, and the goal is that you want to make what's the average advantage of the attacker given an X and the classifier or the DNN model F. You wanted to make sure you wanted to the minimum distance that it needs to add to X such that the classification changes. You wanted this to be as basically as much as possible. So the bigger this value is, it means that attacker needs to add a larger noise. Okay, and that's the expected value of it is they define it as the robustness. The reason I mentioned all this was that they try to do a defense against this attack that try to have a low impact on the architecture, maintain accuracy, maintain speed, and they try to make sure that it send attacks. And they come up, again, as I mentioned, I have lots of texts in case someone reads them, so that's the reason I'm jumping them. Basically, they use something called distillation. And the idea of distillation is that apparently it's used in deep learning to transfer the knowledge of a network trained, let's say, on tens of thousands of samples to another network much quicker. They call it distillation. And you have this initial network that's trained at temperature T, which is based on the T, basically they modified these values a little bit. So there is a modification step here. So they have this training data, they have the training label, and it gives some probability vectors. And these vectors are fed into another network called a distillation network. And then in the distillation network, now instead of original training labels, remember original training label would be like 0, 1. Here now you have a probabilities given here in the distilled network, and you train another deep learning network here, another deep neural network here. So this is called the distillation. And this temperature impacts how much this parameter is modified, how quickly they're modified. So based on this, they claim that they try to answer these questions. They say that does the distillation improve the resiliency? According to that, distillation reduces the adversarial crafting from this to this, substantial reduction, and on the second one from this to this. And this distillation has negligible or non-existing degradation in classification accuracy according to them. And they look at this based on how did they come up with these results. They look at this 9-layer convolutional neural network, and they remember the temperature parameter, they choose 20. And then the distilled network achieved this accuracy on this data set. I think that is out of order. Okay, sorry, there's a mischange in my slides. What is these data sets? One is this handwritten digit data set with 10 classes. We have 0 to 1, 9, 10, 0, 1, 0, 1, and to 9, 10 digits. And then this is color images in 10 classes. You have this for training and this for testing. So this is what they use. And then in this scenario, they basically applied, I'm sorry, there's something out of picture. They applied this pepper-nut attack I just mentioned. And then what they say is that sensitivity inputs, they say that at high temperatures can lead to decreasing of adversarial gradients by up to this factor. In other words, they can resist adversarial gradients much higher in this work, even if the attacker needs to add a much higher gradient. So basically, defensive distillation impacts the average minimum. So the question was, does defensive distillation lead to more robust DNNs? In their work, it increased the robustness for this 7 to 90%. Remember the robustness measure we talked about this robustness measure. So they look at how this robustness measure have changed, and what they claim is that the robustness measure for the first DNN increased 790%. For the second one, it increased almost 600%. So they claim that it's a very fantastic measure. But it turns out that I didn't put the slides here in the interest of time. You can check it. There's a new paper showing that actually this can be easily attacked also. Because once you know, so basically this is robust against the previous attack and the attack on the original network. But when they have a new tailored attack for the distillation mechanism, it turns out that this robustness is not very robust anymore. So it's actually another work on that. So the reason I wanted to add this is that so all these claims are under some assumptions basically. So you need to really understand the assumptions of the defense or the attack things, and the assumptions are very critical here. How am I doing on time? Okay. Basically, there's also a distributed machine learning frameworks applied for malware detection and so on. And they try to look into using machine learning in a distributed setting. So until this point, all of the examples, I just chose this as an example of that. Maybe you don't need to collect all the data into one place and do your models. Maybe you can do a distributed machine learning scenarios. In the distributed setting, what they've done is that usually there is this SVM, and it has binary classification, and you need to have all the frameworks under one root. Now you can do a distributed version of it to solve the problem. So each node, each mobile device may do the part of the learning, and you can combine it to learn the final model. And then what they've looked into is that they look at this MIT Reality Mining is a mobile data set where there are logs from different number of users. They infect half of the data set with malware symptoms, so they simulate the attacks. And then they show that they could, this is the number of, I think, malware SMSs in it. And then their recognition rate after number of SMS in a distributed setting. So this runs on different frameworks. And then they look into computation time for number of clients, and it can change. It's not that much, and the iterations are also doesn't require too much updates between clients per client. The reason I mentioned is that you don't need to have, yes?
With the previous slide, was there a decline after seeing? Is there a reason for the decline? It's an overall, the 1 through 20?
Yeah, 1 to 20.
Yeah, sorry, thought
yeah.
it was.
Yeah. Actually, since I wanted to add a work, people look on network since this was on network school, right? And for network, there was some criticism of all these behavior from this paper, and I think it's very important paper in terms of understanding the practical applications of these things. And of course, here now you can think of other, not only good and bad, maybe you want to do other type of detection, like a misuse detection, where you know precisely the attacks or the attacker behavior or potential attacker behavior, and you want to detect that. And also here you can do anomaly detection, where you just know of the normal activity and you want to detect from normal activity. And what this work argues that you have this well-known problems with the high false positive rate. So the argument is that even if you are applying these techniques for network, if you have hundreds of thousands of connections per day, even 1% can be too much, or 2% can be too much. And lack of free data for training also is an issue. But as we have seen, I think this is kind of attacked. And also, attackers can foil the system to evade detection also in the network setting. I'm not aware of too much work done to look at machine learning. There are some work done on that framework to show that the same things we have just discussed for, let's say, PDF malware or crowd surfing or turfing scenarios is there. And also, the difficulty with evaluation is a problem for the network world. And also one interesting addition is the interpretation of results. And this, I believe, emerging as an important thing, because when you want to do an action, you need to really understand why this black box is saying to you, especially if you have different alarms raised. So this is an active research area in machine learning. My understanding, there is an entire DARPA program called Explainable AI. They start looking into this explainability problem. I think it's an important issue for application to cybersecurity, especially if a cybersecurity analyst gets an alarm, why that alarm is there. And for network applications, there is also this diversity of network traffic that may make it harder to learn models if you apply machine learning. So this work suggests that understanding the threat model is very crucial. And we kind of, I think theoretical results also come into the same conclusion, which is you need to know the attack cost, you need to know the attacker's skills, and so on. So these are not only applicable for maybe network security applications of machine learning, but also in general, I would say, is where do. And I think the scope and the reducing the costs for the deployer could be an issue. And I think this is about deployment and how you deal with the attacks and so on, and depends on the domain. And of course, the evaluation is always critical and understanding the results when you are deploying this for network security. So now the question is why those techniques are not deployed as much? Yes.
So going back to the explainability issue.
Yes.
So is there a general framework for explainable results, or is it very context specific?
So basically, there is lots of active work going on that area. That's also I'm trying to remember. I do some privacy work. We try to look into explainability from like explain the decisions so that it's not discriminate, let's say, a certain group of people. So explainability has some certain nice features for, let's say, for privacy also. There are different frameworks coming in explainability. One example is that maybe you can explain or find a simple rule that approximately captures what this complex model does. For example, if you have a support vector machine with certain kernel that explains voting decisions of the US members of Congress, actually in most cases you can come up with simple rules. So because of this, like if you voted yes to this resolution, then you're a Republican, for example. So you can maybe approximate some rules. There are some work that try to explain a decision based on saying that you have this and this in your feature set. Let's say in this email there was this word and this word and this word. Because of that, we believe the deep learner said that this is malware because this email had Viagra in it. So those kind of explanations are done. In this context, in application to network intrusion detection, when there are many alarms, my understanding is that like how you would order them, and also of course you can order them based on the scores and so on. That's one way, and people are doing it. But if you have some explanation why you think this is an alarm, then it may give more context to the analyst while they are looking into it. So that combination I don't think is explored. As I mentioned, there's also work done on explainability in the context of, I mean, it's active actually, a new DARPA thing on it a couple of years ago. So it's active work in the AI community. But combination to cybersecurity I don't think is explained as much. So actually I'm trying to get a grant from Army, hopefully it was coming soon, on specifically those topics like combination of explainability and adversarial learning. So this work kind of have these guidelines, and this was 4 or 5 years ago, this paper, and he says that because of these challenges, we don't have too much real deployment. As I mentioned, there are many startups that try to change that, and they are deploying all these machine learning techniques for intrusion detection and so on. There are zillions of them coming up. And basically, operational point of view and getting these semantic insights, I think, is the next challenge in deployment. So I think I'm running out of time. So let me summarize. Some of these are my views, so please take it with a grain of salt. What are the lessons learned on all these things? I think what are the summary of all this? You need to really better understanding of the attacker. This is, I think, required for practical deployment to theoretical frameworks. So if you know the attacker, then you can define much more robust techniques, and also you can understand the potential impact of the attacker behavior. And game theory applied, at least in theoretical setting, as a natural tool for such modeling. I believe game theory is also a nice tool for modeling other type of cybersecurity events. There are many other issues that I didn't discuss. Again, this is a very small subset of existing work. I tried to choose the ones that are interesting to me in the literature. Provenance of data, which is where the data is coming from, who touched it, who captured it, has actually a very important impact on applying machine learning data mining for cybersecurity. In many cases, you have class imbalance. This is considered in machine learning a lot, because you may have much more samples of certain type. And there is other work coming out there how can you combine human in the loop in adversarial active learning? How do you get your human feedback in addition to just most of the work I just described was you have the initial samples, you learn a model and you deploy the model. Now you throw in the human in the loop. Maybe human, you can ask from time to time a human expert. How do you get it in the states? And there's some work going on that. So this is, again, this very active area. There are a few other things going on. So it's a service security, right? So I should throw in Sun Tzu Art of War reference. So actually, the insights of this work, I don't think has changed since the thousands of years. And it boils down to if you know yourself, but not the enemy, then you won't be successful. But I think here, if you know the enemy and yourself, you need not fear the result of 100 battles. And this is especially correct for machine learning models, as we have seen, and the models that knows the adversary, potential adversary attacks can be more successful than if you don't consider the adversary. And implications of this is that choosing the features based on the attacker capability and potential adaptation is important. The malware example I was giving, such as any malware detection technique according to these results, at least my interpretation of these results, that looks on the binary, just the binary itself, will be broken sooner or later. Because you can come up with a way to make the binary look like a legitimate binary by using many obfuscation techniques. But if you have a technique that looks at what the malware is trying to do, like the behavior of the malware, we talk about exfiltration, for example, data exfiltration. Malware must need to access the sensitive data if it want to exfiltrate. So if you look at those type of behavior, maybe you will have much more success if you do machine learning, because for successful malware, that will be harder to modify. And similarly, if you look at intrusion detection techniques or intrusion areas, you need to look into behavior more than features that are easily manipulatable. And if you think about the PDF example, the features were easily manipulatable, especially length, this and that, by injecting fake bytes without changing how the PDF is rendered. So from attacker point of view, it was almost a zero-cost change. Of course, robust machine learning techniques that are try to be more robust to this adversarial modification tends to turn better. But still, this features is really important area. And of course, the third main takeaway is that you have more and more data coming. So you need to scale to it. But luckily, this area has been addressed more and more. There's so many open source tools out there, which I will talk about one of my favorite ones in a second.
So this goes back to the previous questions. So when you say robust machine learning techniques, are there rules of thumb?
So basically for SVM, for example, we have seen a couple of versions where they try to modify the support vector machine. Such that it can withstand certain data corruption type of attacks. So they are clearly much more robust under attacks than the normal one.
Robust per specific things they assume the attacker will do.
Their assumption is that attacker can change a certain feature by this much. It doesn't really know what attacker will do in practice. So in a sense, for example, if you can say that attacker can change this feature, but not this feature, or this feature is more changeable than this, those assumptions is good enough for those models. But of course, if you have in the image example, attacker can change every pixel. So that clearly those techniques wouldn't be applicable to image because all the features are changeable. But in the network setting, for example, it may be harder for attacker to change the protocol number if it's on HTTP, or port number, for example. Right? So there are some features that are easier to change versus harder to change.
Is there a trade-off between robustness and learnability? Could it be that if I make
yes, there's a trade-off. There's a trade-off in some of the examples. Basically, if I go to this one, okay, actually it's worse. I don't see it. Let me give you an. So in this example, the blue line was more robust version. It was going farther away from the bad points, more closer to good points. So what happens is that if you choose the line here, okay, based on to be more robust, but in the regular deployment, you would be misclassifying many of these green points as bad points. Okay, so therefore, understanding attacker capability is an important factor here. So therefore, you can be more robust, which means that you are more things closer to the boundary. You may say that, oh, this is attack, this is attack. So you would not miss the attacks, but of course now you are making more error on the type. So there is a trade-off clearly. That's the reason understanding capability part is relevant. So this feature, again, we mentioned this already, like hard for attacker to manipulate and indicative of attack. Behavioral features was an example in the malware setting. I think you need to maybe try different tools in practice when you're deploying these techniques. One tool is usually not very good enough. And as I mentioned, these deep native networks are very costly and you need lots of data slash. Training them takes so much time. I just needed to buy like a $5,000–6,000 machine to throw in more GPUs to do even a simple setting. And also there are different other tools that you can try. But again, if the feature set is right, according to my belief, even random forest could be a good choice. Now the question is, sorry, I didn't see.
If I were to draw a parallel to, like, system security,
Mm-hmm.
there what you have a choice between security and performance, more or less, right?
Mm-hmm.
So I could compile C with lots of guards and catch all buffer overflows and stuff
Mm-hmm.
like that. I could do tail tracking and
Mm-hmm.
differential information, flow control, whatever.
Sure.
Right? Is there such a trade-off here, right? Like, will these techniques to defend against adversaries, will they make it much more difficult to actually run the classification? Will they increase the, by X times the classification overhead or whatever?
Mm-hmm. I think in practical deployment, what you are seeing is that, as I mentioned, one tool usually doesn't work just enough. So you have multiple classifiers. I had one example where we built different classifiers for different type of attackers and we use them in ensemble setting. So you would have probably would build many classifiers that are tailored against different type of attacks and different type of adaptive behavior and use them in conjunction. Again, I didn't deploy them in practical things. So therefore, I expect that the cost will increase to be more robust because of all this. You need to be capturing all these variations. But that's the active area. In other words, what's the right deployment setting? So for each given, you have theoretical results, you have those kind of results. But what's the right deployment? And I think the right deployment is that you will have layers of classifiers that looks at different things and different type of attackers. And eventually you combine them. So how many layers, what's at each layer, I think it will be active research / deployment specific. For efficient data, how do you process the data? There are open source tools are happening on this domain. And actually there's a new one, I forgot to add it here, that try to be specific for network intrusion detection. Apache, I think Metron is coming. I will add that link to the citations to look at it. So there are many. The nice thing is that nowadays this is quite automated. You can do all these analysis. My recent, we are in our group, we are using Spark. I just give an example. You don't have, I mean, as a one big learning framework. Why I like Spark personally, it is distributed in memory, so it's usually run faster than Hadoop and so on. If you have reasonable amount of data, and it has nice set of libraries on it, and it has MLlib that has a basic machine learning functions. And then it has also libraries we use, for example, for graph processing and also streaming. If the data is coming, like if you have network packet coming, you can do streaming processing. And also, new addition by Intel, they announced it I think a year ago or so. They have also something called BigDL for deep learning. So now Spark has deep learning libraries on it. So you can have a distributed in cluster big data processing with also deep learning. This new tool supports deep learning. It's very efficient deep learning model. And then apparently Intel boasts about this, like they claim this Intel Math kernel library is super duper, make it fast on Intel. Of course, you need to run on Intel CPUs. For making it faster, and apparently I think I will double check this, but I think they also have support for GPUs, so you can have a cluster of GPUs on top of Spark that can do deep learning. As I mentioned, our experience is that if you have a low dimensional data, what is low? It's domain specific probably. Random forest SVMs, adversarial SVMs, for example, works well enough. In other words, it has similar accuracy compared to deep learning. But if you're doing image especially, those kind of things, clearly deep learning is the way. So I'll stop here. I want to thank my funding. This was funded, some of it was our work. It was funded by US Army. So I want to thank them as well. Thanks.
Any more questions?
Yes.
So you alluded at one point to the difficulty in evaluating how well learning techniques work for intrusion detection.
Mm-hmm. Yeah.
But there are, like you also mentioned, a lot of industry efforts, at least startups, trying to do that. So how are they trying to quantify how well it provides any benefit that's useful? Yeah,
that was a thing. Like whenever I wanted to get the data from companies, for example, like in Dallas area, AT&T is base headquartered in Dallas. I have some people in AT&T. They don't give us the real data. Never give us. But it turns out that when there are startups and they have VC funders and they call some guys in the CEO's office, I guess, and then they manage to get a non-disclosure agreement and get the data from them. And then, so they claim to have access. I've seen some white papers from those companies. They claim to have access to real intrusion detection. And then they usually say that, for the attacks that they figure out later on. So usually they are given data set, and then there was intrusion later on figured out by some reason. For example, for credit card companies, eventually you know that you were hacked because Visa calls you. Why? Because many credit cards passed by your system is now stolen. So it must be your company. So they know in the future that they somehow detect the attack because of these kind of things. Like that's how actually Target attack was detected, because the Visa figured out that all the credit cards swapped at Target, which is a big department store in US a couple of years ago, turned out that have a malware on all the terminals, credit card terminals, and that malware was copying the credit card numbers. So anyway, so they somehow get this data sets from these companies. And then the company, then they, on that data set they run, and then they claim that we have 90% accuracy, 99% accuracy. But again, it's with grain of salt. I mean, we've seen papers like the PDF rate paper, right? It was 99% accuracy, but when you have a targeted attack, it wasn't 99% anytime. So no one, as far as I know, none of those startups need to withstand a targeted attack. And many of the work is not published, or even if it's published, some of the important details are not there. And they don't have this adversarial evaluation component in it. So they are a startup and they need to sell products, right? So they hype it up, I think, of their capabilities. But usually they have, apparently they say that nowadays if you have deep learning or blockchain in your startup technology thing, it increases your value in cybersecurity by X%. So those are the keywords to throw in, and you will.
We're covering all of these today.
Yeah, exactly. So machine learning, deep learning, and blockchain, I think, in the afternoon session. So that's the other aspect. I think they wanted to do things. Yes.
Does the vagueness of security also help like machine learning?
Sorry?
Even if you have like the 20% of the attacks you find, that's because in security you say we will reduce the amount of attacks by 20%. It's a good thing. For machine learning, it's like core. You know, you can frame it very well.
So you mean the framing of the problem, or
framing of the results of the machine learning?
Yeah, I mean, but from a cybersecurity, I wouldn't agree that 20% is like 20%. If you only catch the bad guys 20% of the time or 30% of the time, it's really bad, right? They already will be successful. So I think the other way to answer the question is that the interaction maybe will allow much more robust machine learning techniques. So I think there will be lots of synergy in the area. So the framing, I guess, if you want to sell a product, I think that's how you would frame. So if you're a startup, but yeah, yes.
Is there any analysis about the success of the attacks on neural networks on models that were trained as generative adversarial networks versus more classically trained?
I think the guns were also Goodfellow's work. I think they were, right? Do you remember? Anyway, if I'm not mistaken, one of the attack guys, one of the attacks I mentioned is from the people who look at the generative adversarial networks. But the generative adversarial networks, as far as I know, is to way to come up with a good synthetic data generation. It's not really against attacks as well. The goal for the guns, if I recall correctly, is that you try to come up with a synthetic data input and a network so that the output cannot be distinguished from real versus synthetic. So it's a generation of synthetic data that cannot be distinguished from the normal data. So therefore, I'm not sure it's really applicable to these settings, as far as I know. But if it is, I think the guns were first suggested by Goodfellow, and one of the attacks are from him. So if there's a connection, I think you've done it already. Let's check the literature. But I'm not aware of that.
Okay.
Good.
Thank you.
Thank you.